Okay, so let's start. We touched last lecture kind of toward the last eighth of the lecture on compensation. So since it's kind of a tricky thing, I'll kind of cover the basic principle again, and then we're going to go into sort of more advanced schemes with pole splitting and things like that. So what we had last time was the amplifier system that had 3 poles. And then we were drawing the Bode plots for A of j omega versus omega log. And at every pole, we would get like minus 20 dB extra slope. With this being 20 log 10 of A0, right? And then if we looked at the phase characteristics, this was the angle of A of j omega. We were going down by 90 degrees at every pole. And here we go down something like this. Okay, so that was our phase characteristics. And then we looked at the point where the sign of the gain changes. And we're saying that's a critical point. The frequency we'll label omega 180. Because at that frequency, the gain flips. So the phase is 180 degrees. So your sign of the A0 flips. And the important thing was that at that point in time, or in frequency, if your forward gain, which is the A of j omega 180, is stronger than 1 over f, then your total A times f is actually going to be bigger than 1. And your total loop gain is bigger than 1, and you get instability because you're passing now the signal in a positive feedback back to the input of the amplifier. Right, so it was important for us to look at where is this curve, which was 20 log 10, 1 over f, which was essentially 20 log 10 of our loop gain, A naught, of closed, not the loop gain, but closed loop amplifier gain, A naught. Right? Because in high gain amplifiers, if you tie a loop back around them, then the closed loop gain is really defined by the F, which is the feedback factor, right? Not the gain of the amplifier itself. And we said that this over here was essentially the loop gain. Right, so you start with loop gain being very large, but the sign of the whole of that loop gain is negative, right? Because of the minus in the feedback loop. And then you go down, and eventually that loop gain changes sign because of this minus pi, but you want to make sure that at that point you don't have this loop gain greater than 1. In this case, we have instability because here we're still greater than 1 in the loop gain. And so we call that negative gain margin. This is here we would say negative gain margin, right? If we had another loop or another set of coefficients where we would cross right here, then at omega 180, we would have this much of margin, and that would be our gain margin. Right? Or in other words, if we look at where the crossing is, it would be here. So that's where gain is, loop gain is 1. And we look at how far away we're from pi. So in that case, this would be phase margin. That is roughly around 45 degrees, pi over 4. Right. So those were the basic definitions, how we analyze the stability. But once we analyze it and we figure out we're in trouble, we have to do something about it. Right? And so in this previous case, let's say we're in trouble because the gain margin was negative, or even if you look at where your unity gain is, you're roughly at pi over 4 phase margin, right? So that's a problem. Okay. So we said that the way to fix this is to do compensation, and we could add a pole to this system that would early on basically start breaking this transfer characteristics at minus 20 dB per decade, so way earlier than pole 1. And as long as I pick, for example, pole 2 to be my crossing point, or in this case, I would have to, if I add a pole, I would have to actually pick pole 1 as my crossing point. Then I would always make sure that at pole 1, I have enough of a phase margin. Right? Because at pole 1, I have already decreased by 90 from the dominant pole that I've added, and then I have another 45 degrees that I come down. So I always have pi over 4 phase margin. But adding this dominant pole would kind of make our usable bandwidth, unity gain bandwidth of the amplifier, be kind of at P1, which is very low. Because we're adding extra parasitics to our circuits that we're not really leveraging what is already there. Right? So the other idea that we mentioned toward the end of the class was, OK, why don't we just find where this P1 happens and boost it a little bit? Okay? So we make sure that we shift this P1 over to an appropriate place so that then P2 really is the one that provides the crossing. So we're going to have a situation here that we go in parallel. This has to be 20 dB per decade slope because it's only originating from this new location of the pole. This is going to be P1 prime. So our pole 1 has shifted all the way here. Okay. And if that happens, then you start breaking the phase right over here. You come down to 90. And then you're OK up until you start hitting pole 2. And then you go and shift by another pi over 4 until you hit pole 2. And then you're guaranteed this pi over 4 margin. Because you're on purpose making the unity gain loop gain exactly at pole 2. Okay? So in that way, you have more bandwidth because now your unity gain bandwidth is at pole 2 rather than at pole 1. And you haven't added an extra pole. So because pole 1, to shift pole 1 to this P1 prime is less capacitance added to the circuit because pole 1 was at a higher location to begin with. You can now do this a little bit more efficiently. Right. So, but how much should you shift? So what is the new value of P1 prime? If you know that you are riding on this curve of 20 dB per decade, and you know that you want to hit, you're hitting A0 when you stop. And you start from 1 over f. So but how much do you have to go back? Any takers? Guesses? We want to use P2 as a reference, right? So from P2 we want to move. By how much do we move? $180 what? So remember what we talked about when we talked about the unity gain bandwidth, right? For a single pole amplifier. We had this curve that was 20 dB per decade. And however much you move from the unity gain, that's how much in frequency back, that's how much your gain increases, right? So here, we want to move so much back that our gain increases by how much? From 1 over f to A0. So by how much is that? What is this difference here? We're going to assume that we're pushing here into the region where this gain curve is flat. It's at A0. So we're looking at the ratio of A0 and 1 over f. So what is that ratio? Right. This thing over here, let's mark it as a star, is a difference of 20 log 10 of A0 and 20 log 10 of 1 over f. Right? So that is 20 log 10 of A0 times f. What is A0 times f? A0 times f is our DC loop gain, right? So that was the thing we called T0. Right? So starting from this position, I want to move back at 20 dB per decade and span this gain region of A0F. Right? So by how much do I have to move back? 20 dB per decade just means for every 10x in frequency, I get 10x gain. Right? So if I back off from P2 by 10x, I increase my gain by 10x. Right? So my A0, my AF becomes 10 because I'm starting from 1, right? And I want to go all the way to A0F. So how much do I have to go back? A0F. Not that hard. Okay, but it's important to kind of keep this in mind. Okay, so this is the basic compensation. Okay, what we've been assuming here is that while P1 is moving back, P2 stays in the same place, okay? And with the things that you've done in the lab, and we're going to do a quick example of that as well, this is sort of the case. If you have this one dominant capacitor you're adding somewhere to create a pole, the others are not going to move by much, okay? And so you can kind of do calculations this way to figure out what your P1 previously was, and then what you need to add to move P1 to P1 prime. It's basically this new value, right? So you can go and do the calculations. What ends up being the case is the C's that you add are kind of on the order of 1,000 picofarads. Okay. Let's make this pico, which are some pretty large values to be adding to sort of integrated circuits, okay, in terms of capacitance. So let's do a quick example just so it kind of gels in a little bit better. Let's say we have a two-stage differential amplifier. And then we're going to have the second stage. Then I'm going to take a single-ended output. I mean, for all intents and purposes, we can keep this one also loaded. Doesn't really matter that much, but just not to confuse you, let's say. So this is going to go output stage. Okay, and then what we have is these two we're going to take differentially and plug in. So this is like VI1, VI2. And then we're going to take this one and feed it around to this gate. And then the other one will go here. And we're going to say these are, let's say, Q3 and Q4. So if you want to analyze this circuit, what's happening in the differential gain mode, then VI1 will be VID over 2. VI2 will be minus VID over 2. And then we can do a half circuit differentially. So we'll ground this node, and we'll get over here, we're going to have RL1. And then that goes into Q3. This is also grounded, and there's like an RL2 over here. And the same, and then this is the output. And the same thing is for Q2 and Q4. So I'll actually draw those two rather than the other two. Okay, but half circuit is exactly the same. So over here, we're going to have several poles, but the dominant one that, or the The largest one, sort of naturally, will be the one at this node over here, simply because we have the capacitance here, which is C pi, plus we have the C mu coming from over here. Right? That is going to Miller back into what RL1 sees as. So if we were to compensate this particular thing by kind of adding more capacitance to move pole 1, we would want to do it exactly at this point, because we're already having that pole to be dominant. So we just want to add a little bit more in order to shift that pole down to where we want. So that was this situation over here. We've identified this pole 1, and then we just want to now move it into P1 prime. Okay, so what we're going to do here is add a capacitor here. Now, the capacitor that we add here to ground, in the first stage, we're adding to the collector of the half circuit, right? So it looks something like this. Okay, and then we're assuming that there is a ground here, just because the output is purely differential to differential input. Right? That was our half circuit, the way we derived the half circuit. So if I was to put here a capacitor, so another one would have to come from the other side as well. So in the differential mode, there will be ground here, but I'm just not going to draw it. So for this whole thing to be C, what does this one have to be over here in the half circuit? What does each one of these have to be for the whole thing to be C? I don't know why it's doing this. Okay. What does each have to be so for the whole series thing to be C? Double. So this has to be 2C. Okay. So now we have our circuit. So let's say C that I'm adding has to be reasonably larger than your transistor capacitances. Keep in mind that I have to shift by pole divided by A0F. A0 is pretty big sometimes, 100, 1,000. So this has to be reasonably bigger than all the other caps in the circuit. So then I can use the open circuit time constant or zero value time constant to say, okay, what is it, the new pole that this capacitance sees, right? So in that case, I can say that the dominant pole now, or this is, we can call this P1 prime, is what? Okay, we have 2C, and then what resistance do we see from 2C? Okay. That's, I mean, we can write it, okay, RO2 in parallel with what? RL1. And then plus if there's some RB, okay, that will be there as well, right? Let's label this as 4, right? Okay, so RL1 is typically a lot smaller than RO2 because that's just our load resistor, maybe a few kilo ohms or something. R pi is going to be approximately that as well. So for that pole to shift by a lot down, this C has to be reasonably big. So this C will have to be kind of 1,000 picofarads or so. Okay. So in order to decrease this cap, instead of placing it like this, we could try to use the Miller effect. Okay? And all that the Miller effect says if I have an amplifier and I have C over here, or any impedance, right? We covered this kind of when we did single stage stuff. Then this is equivalent to having some other C here lumped to ground and A. At least at this node, the equivalence is that this has to be something like this, right? It's assumed that the gain is negative here. And for our single stage, you would get something like GMRL1 or something like that, right? Or 2, right? Or GMRD, it's all the same, right? Or minus G, right? So then essentially your C will be boosted by, will be sort of amplified by the gain of the stage. If the gain of the stage is 10 or 100, there you go. You can use 100 times, 10 or 100 times smaller capacitance to do effectively the same job, right? So we could call this CM for similar, and then this will be our C that we wanted to, or 2C, that we wanted to use in this case over here, right? But in that case, we don't want to put 2C over here. We would put it over here. So this would be CM that we put in instead of this capacitor over here, right? There is another side benefit, and we're going to do in a minute kind of a derivation so you can see that. There's another side benefit of doing the Miller, and that is that when you do the Miller cap, you're not only in the sigma plane, we can label P1 and then, okay, P2. You're not only moving P1 to P1 prime, which was our goal in compensation. We wanted to move P1 to be smaller magnitude pole, right, to P1 prime. But what happens is that by the same token, P2 moves to P2 prime, because this C sort of couples the two poles together. Okay. Previously, if you put just 2C, you're kind of isolating this additional cap only to affect one pole. But if you put it across, you're kind of affecting both. Okay? And we'll do this in a minute, kind of in a more detailed derivation. But in a nutshell, that's kind of the side benefit. So pole splitting is a side benefit. Why is it a side benefit? Well, we just pushed our critical pole, P2, like away. Remember that in a closed loop, that will be your pole, right? So you've just increased the bandwidth of your closed loop system by doing so, right? And you've also gotten a lot less capacitance to add to the circuit, so now you can think about something that's an integrated circuit. You're talking about C millers of approximate, let's say 30 to 50 picofarads. In fact, the early op-amps that were integrated, or the first ones, analog devices, had really roughly about 30 picofarad capacitances and exactly use this type of effect. Okay, so let's take a look a little bit at the derivation itself, just so you can understand where things are coming from. We can, so this is small signal model of two-stage amp. Let me just change the. So what we have, we can model the transconductance of the source from the first stage as some IS, and then we'll add R1 will be kind of the total output impedance of the first stage. Then we have some capacitance at the output of the first stage. This is sort of where we used to add this extra capacitor C, right? But now we're not going to do that anymore. And then you have this CC, which is, or let's call it just C, which is the bridge capacitor. And then we have a controlled source. We're going to call it GMV1, with V1 being this voltage over here. And then we'll have C2 and then R2. C2 is, again, the load at the collector, the capacitive load at the collector, and the R2 is the resistive load at the collector, or the output stage. And we get VO over here. So we'll just do, in order to capture both the pole and zero behavior, we'll just do a few KCL, KVL kind of things. So from KCLs at this node over here and this node over here, we can write two things. So minus IS equals V1 over R1 plus V1 SC1. That's this current. And then we'll have a difference going through the capacitor. We can call this, IC. Okay, so that will be the first KCL. And then the second one comes from GMV1 plus V0 over R2 plus V0 SC2, all the currents going down, and then plus V0 minus V1 SC equals 0. If you do the math and kind of take out V1 from both of these equations, you get something that relates VO to IS. And because IS is just some first stage transconductance times the input voltage of the first stage, that's really your gain. Okay? So this is just the overall transimpedance of the amplifier. And what you'll get is the following. GM minus SC, R1, R2. And then over here we have 1 plus S. And then C plus C2 times R2 plus C plus C1 times R1 plus GM1 R1 R2C. And then plus, and we have the factor with S squared. And that's R1 R2. Then C1, C2 plus CC1 plus CC2. Okay. So what we can say from here immediately is that we have our right half plane 0. Okay. And that 0 is coming from here. It's GM over C. You sort of think intuitively about this one is that at high frequencies, this C becomes a short. Okay? So it will essentially feed the signal directly from the input to the output. It's kind of shorting the second stage completely. So there's no sign inversion. Normally, the second stage from base to collector or from gate to drain would have minus GM times whatever the load is, right? But here, the current will just shoot straight through, right? So the signal, the phase between gate and drain or body and collector will basically be 0, okay? So therefore, you do have a short path and not something that kind of can get attenuated at high frequency. So that's this right half plane zero. Right half plane zeros are kind of interesting. They boost your gain, right? But at the same time, they break the phase is negative, right? And that will actually be very bad for us, as we'll see later in CMOS op-amp, because that's exactly the behavior you don't want to have. You want your gain to be lowered and your phase to be maintained, right? Because we want it to decrease the gain below 1 over f in order to have gain margin. But what this does, it keeps your gain kind of flat instead of breaking it, while it drops your phase more quickly to pi, right? So then you quickly run out of phase margin, and you're left with pretty high gain for the loop gain, and then you're unstable. Okay, so those are kind of the things that we're going to look in the next week or so when we look at CMOS. But for bipolars, it's very high. For BJTs, right? So not important. For CMOS, is critical. And this is also because, you know, when we looked at GMs of CMOS and bipolars, we saw that GMs of CMOS are way lower, right, than in bipolars. So then this zero will be way closer to our pole 2, and in that case will really affect the phase margin that we're trying to create right there. Because remember when we did the compensation at pole 2, we wanted to have this pi over 4 margin, right? But if there was a zero, right half plane zero very close to here, it would break this even lower, and therefore you would lose this pi over 4 margin, while the gain would kind of stay the same. Okay, so that's kind of this bad behavior in CMOS that we'll look at more. Okay, but for now we're gonna, because this is a bipolar example that we're talking about, we're gonna kind of neglect it. So in the end of the day, if you look at any polynomials of this form, you get 1 minus s, which is the sum of 2 poles, plus s squared over p1, p2. So these identities we're going to use to kind of look into these expressions for s2 and s squared and s, and then read out pole 1 and pole 2. Okay. So if p2 is much greater than pole 1, like say 5, 10x, then we can do kind of, we can read out simple things about this. So this is same as OCTC for at least pole 1. And this will be minus 1 over R1 C1 plus C plus R2 C2 plus C plus GM R1 R2 C. So what we've done, we really just took the whole thing and made it pole 1, simply because that is like the sum of reciprocals, and if P2 is like super big with respect to P1, then this is mostly just 1 over P1, right? And then we can say if C is reasonably large, then really this factor is the one that dominates, meaning C larger than C1 or C2, which are just transistor kind of parasitics, right? So this is then approximately just minus 1 over GM R1 R2C. If you take pole 1 to be this, then pole 2 we can derive from this piece over here, that this thing that's with s squared is really now a product of P1 and P2. And P1 is just this. So then P2 will be minus GM C over C1 C2 plus C times C1 plus C2. Okay, now things get interesting. Okay, If you take a look at these two expressions, what happens with pole 1 as C increases? Okay. So C increases. What happens with pole 1 in magnitude? Gets smaller. So pole 1 magnitude decreases. What happens with P2? Yeah, because I have this constant factor over here, my numerator is going to grow faster, right? So the magnitude of P2 is actually going to increase. Okay. May not increase by a whole lot, but it will still be increasing. Okay. So this is exactly what we call pole splitting. Right? So by me adding this C from CGD or C mu, turning it into something that's 100 times more or 1,000 times more, now I actually start splitting the poles. Okay. So let's take a look at sort of some expressions for that. If we draw kind of the sigma now versus j omega, what we had was a pole 1, which was at, let's say, okay, I'll draw pole 1 and pole 2. And if we assume that C equals 0, meaning C is very small, right? I'm neglecting kind of the Miller effect of that C mu. And we go back to this circuit over here. Okay. So if I say C0 is very small, I'm not going to neglect it. What is the pole that I have on this side over here? It has to come from this capacitor. And then what resistance do I see if this is gone? Right? So I only see R1. What does C2 see? Independent sources are off. This is 0. There's no current source here. So C2 sees only R2. Right? So if C equals 0, then pole 1 is going to be minus 1 over R1C1, and pole 2 will be minus 1 over R2C2. Those would be kind of my approximately original locations, right? Now that I've inserted this big C, okay, then I'm shifting to these poles that we just mentioned, right? So pole 1 will be moving to minus 1 over GM R1 R2C. And you see that the shift has happened by GM R2, kind of, right? Because you've moved by that much with respect to R1C1. And then P2 will be moving by minus GMC over C1, C2 plus C times C1 plus C2, right? That was the P2 prime and P1 prime. Okay, so this is this pole splitting that we wanted to use. So again, consider that we, for example, didn't use this type of Miller effect. Okay, so let's say we just said, well, in the previous diagram, why don't we just increase this C1 so that that's the capacitance between the first and second stage? Why don't we just add our compensator like that, which is kind of the same thing that we did over here, right, with 2C. So let's see how things would look like that then. Okay? So I will have then the situation where pole 1 is -1 over R1C1, because it will be definitely the most dominant pole. I can sort of neglect C from the Miller, because that would just be C mu feeding back. Right? And then from the equations that we already derived for the true pole 1 and 0 and the product of these two, I'll get essentially that P2 is 1 over R2 times C2 plus C. Okay. And for small c, because c was approximately just C mu, that was just a transistor C, then P2 would really just be approximately the same as the one that we did here. Right? So what this is telling you is that as I'm increasing C1, pole 1 is dropping, but my P2 is staying pretty much at the same point. Right? And instead, it could have gone to minus GMC over C1, C2 plus C times C1 plus C2. Okay. So now that you have by how much each shifts, both in the case where you want to load it with C1 or you load it with C, now you can go back and do the same compensation trick. Say, okay, well, my P1 prime really wants to be P2 over A0F. So this is the case where C1 increases. And in case where we increase C, we want to have our P1 prime be actually P2 prime over A0F. Okay? Because now our P2 is also moving, right? So as P2 is moving over there, I can move my P1 less to the left, right, to maintain this same ratio A0F. Okay? And then in a given context, once you know what your A0F is, for example, stuff that you will do next week in the lab, this week you sort of had to calculate C1, which is the big load, or we gave you 680, but you have to kind of measure what's going on. Then next week, when you calculate the CM, you can use these tricks to figure out how much you want to stabilize it and how much that CM now has to be. But you have to take into account that, now you're moving P2. Right. Notice that moving P2 to the right is doing nothing to the phase margin, right? Because you've already dropped by 90 degrees at P1 prime, and then you're extending, and when you hit P2 prime, you're going to drop by another 45 until you hit, and then you know that at that point your gain is also crossing 1 over F, right? This is A0, or A. And because of that, you always are guaranteeing pi over 4 phase margin right over here. Right? So it doesn't matter that I've kind of stretched this a little bit or shifted it in frequency. What matters is that I'm guaranteeing this phase margin here of pi over 4 by locking myself to the second pole. Okay, so that's all for today. And I think next week we're going to look a little bit more into CMOS op-amps, like first, second stage, look at some of the basic variants, and then look at some of the higher gain variants. And then we're going to come back to this compensation for CMOS flavors. Because, as I said, some of these tricks that we're doing It's not going to work exactly out of the box for CMOS, simply because of this right half plane 0, which we could neglect in bipolars, but we cannot neglect in CMOS. So we'll have to do a little bit more complicated compensation over there, but you'll kind of understand it when we get to it. OK.